So today we are looking into linear maps between vector spaces V and W. These are assumed to be K vector spaces where K is a field, for example the real numbers. And the kernel of this linear map is defined as all vectors which are mapped to 0 by this linear map. Or alternatively you can see it as the pre-image of 0. The pre-image of 0 which is an element of W. And the pre-image lies inside the vector space V. And we want to show that the kernel is a subspace of V. For this, we need to prove or check three properties. First, 0 is inside the kernel of phi. But this is easy to see because 0 is always mapped to 0 by linear maps. So you can see it like follows. Phi of the 0 vector is the same as phi of 0 times 0, where this one is an element of the field K, and this is still the same vector as part of the vector space V. And because phi is linear, you can, and this is very important, you can take out factors. So you have 0 times phi of 0. And still, this is an element of the vector space V, and this is an element of the field K. So phi of 0 is any element of the vector space W. So we have 0 times any vector from a vector space W, and this is always 0 because W is a vector space. And here it holds 0 times any vector is 0. So this is true. So the kernel is not empty, it contains at least one element, and this is 0. So for the next property, we need to show that the kernel is closed in the addition. So let's take two vectors from the kernel, v1 and v2, from the kernel of phi. And let's check whether the sum also lies in the kernel. And for any vector to be in the kernel, we need to check whether phi maps this vector to 0. So let's check it. So phi of v1 plus v2, that's what we need to check, whether this is 0, is equal to, because phi is linear, is equal to phi of v1 plus phi of v2. And because v1 and v2 are both part of the kernel, they are both mapped to 0. So this is 0 and this is also 0. So we have 0 plus 0, these are two vectors, the 0 vectors inside the vector space W, and this equals 0 as well. So we see that the sum of two vectors of the kernel is also part of the kernel because the sum is also mapped to 0 in this case. And now let's check the third property. So for this, let's take any scalar element of the field K and any vector from the kernel of phi. And then we need to check that the kernel is closed under scalar multiplication. So meaning lambda times v also needs to be part of the kernel. Let's check whether this is true. So let's apply phi on lambda times v. And again, we can take out lambda. So we have lambda times phi of v. And this is true because phi is linear, of course. And because v is part of the kernel, this is exactly 0. So we have lambda times 0. And because 0 is part of the vector space W, and lambda is part of the field K, and W is a K vector space, this equals exactly 0. So we see that the kernel is also closed under scalar multiplication of the field K. So all in all, we prove that the kernel is not empty, it contains always 0, it's closed under addition of vectors, and it's closed under scalar multiplication. That's what we showed here. So if you are further interested into topics like matrices, linear maps, linear subspaces, kernels, images, and just linear algebra in general, please hit the subscribe button, comment the video, like the video, and stay tuned for more. Thank you.